All right. So the recorder is on. Sorry? Sound, double check. And it's good. All right. Okay, so we are moving on to a new topic now. Okay, and for those of you who are kind of wondering what are the answers to the exam, I talked about it last week after the exam. So if you check out the video of that day, it should have the key or the answers already. And some people were there too, just to make sure that I did not, I did not think that I did it, but I actually did not do it. Yeah. Okay, so I'm pretty sure I did it. So we talked about the solution already, and I am in the process of grading it. The first 3 questions are now graded. They are in the form of a homework assignments, because that way I can use a rubric, to clearly indicate, how you score with each criterion, that I have for each question. Okay, so when you look up your grade, you should be able to find out your respective, point values for each question. At least for the first 3, I'm still in the process of grading the rest. I have 3 classes, all having exam 1, in the same week. In fact, in the same 2 days. So it will take me a while to dig through all that stuff. But for this class, we are moving on to non-integer representation. Okay, so this particular section, which I'm supposed to spend 3 hours on, which is just about a week, a week's time, is on fixed number and floating point number representation. And as you might, notice, there's a new homework assignment already. It's called ATOF, or ASCII to floating point representation. Okay, so I'll talk about that maybe halfway through today's lecture. Okay. And then in today's lab, I will also help you guys figure out a general strategy of how to implement the program. This is all going to be written in C, so there's no assembly language programming with this one, and it's not an extension to the processor. Okay, we're not going to add an FPU, a floating point unit, to that particular processor. that might be a little bit of an overkill. Okay. So what we'll do is we'll talk about fixed point representation and also floating point representation, and we'll talk about these two and look at we'll look at the representation first, and then we'll talk about operations related to the representation. All right. So at this point, we have talked about integers. We have talked about signed integers, how to represent positive as well as negative values. Is that okay so far? Okay. So the next question is, but what about non-integers? What about 1.25? Okay, 1.25 is not an integer value, but you might want to be able to represent that value also, right? So give me one reason why we may have to deal with non-integer values in real life.
Money, transactions, money banking.
Money banking. Now money is kind of a special case. It's kind of a special case because you can always go for the smallest denominator, and then you just say, instead of counting dollars, we can count cents, or a tenth of a cent, for rounding purposes. And that's actually how banks do it. They actually represent the exact value in terms of fractions of a cent. So this way, there won't be any rounding issues. Yeah, go ahead.
I was just going to say precision.
Precision, okay. Go ahead.
Any sort of like scientific or experimental data.
Excellent. Okay, any type of scientific related calculations. Okay, that's why when you have a scientific calculator, how do you enter a really, really big number? Scientific notation. Okay, the scientific notation is a floating point number already. Okay, so we'll talk about what that means. But before we go that far, okay, let's go back a little bit and talk about how we can represent just really simple non-integer values. Okay, do you still remember the analogy of using using 1, 2, 4, 8 dollar bills?
Yeah.
You still remember that? But what about on the other side? In other words, on the integer side, we have $1 bills, $2 bills, $4 bills, $8 bills, and so on. But occasionally you want to be able to specify a smaller amount of money. So what about the other side? What is
25 cents.
A half dollar, okay?
Quarter.
A $0.25, and then in this case, we have an eighth dollar, because these are all powers of 2 as well. 0.5 is 2 to the power of -1. 0.25, which is a quarter, is 2 to the power of -2. 2 to the power of -3 is 1/8, which is also 0.125, okay, and so on. So that means it works in both directions. This is 2 to the power of 0, 2 to the power of 1, and so on. Okay. So one way to do this, if I am managing a bank, okay, and I need to keep track of how much money you guys might have in a bank, I can just say, okay, if this is the smallest unit of money, then I'll just have to count the number of eighth dollars, for everyone. Now, if I count that, how do I know the actual amount of dollars when you give me a number? Okay, so let's just look at this number here. So let's say. So let's say this is the quantity of eighth dollars that you have in a bank. Okay, that's representing your savings. Okay,
Is that a 4 or a 1?
that's a 1. Sorry, it's a 1. Bad penmanship. Okay, so if this is a binary number and it is, let's say this is signed, okay, and this is a 32-bit number, and the rest are all zeros, so you're not owing the bank any money. You're actually having a savings of positive, non-negative number of amount. Okay. How much money do I actually have in terms of dollars? Now remember, this is representing the number in eighths, right? So this is still representing eighths. This is representing quarters. This is representing halves, right? So that means the implicit point, okay, and I won't call this a decimal point because it is not a decimal number. So if you want to, you can call this a binary point. But this is the point where it breaks the fractional part from the non-fractional part. So this is a 1, 2, 4, 8, and you know the rest, right? So this is how we can represent a non-integer value by assuming, okay, a point to be at a particular position between 2 bits. But that's really just an assumption, okay? This is never actually, stated, okay? It's just understood by whoever is writing the program that we'll put a point between the 3rd and the 4th digit from the right-hand side. And this is the essence of fixed point representation. Yep.
So we never get to like 1/16 of a dollar?
You cannot represent 1/16 in this case because the point is fixed. You cannot move it around, and since the point is always here, there's no way to represent any value smaller than an eighth. Okay, that's a good question. Yep.
Can you also use like 2 bytes? 1 byte would be to the right of the decimal point, 1 byte would represent to the left.
We do not use that method. We just look at the number as one big chunk of zeros and ones, and we don't really break it up into 2. At least not with fixed point numbers. Now with floating point numbers, we break it up into multiple parts. So are there any other questions about the representation of a value using a fixed point representation? Now, I'm not going to talk about multiplication and other arithmetic operations using fixed point calculation at this point because I want to move on to talk about floating point numbers. Okay? So when you look at this particular way of representing fractional values, it is really nice from multiple perspectives. One, it is simple. Okay? It's just one assumption that we put a point between bit 0, 1, 2, and 3. So between bit 2 and bit 3, that's an implicit point. And we are implicitly basically saying the least significant digit is representing how many eighths we have. So it's very simple. It's quick to calculate. Addition and subtraction using a fixed point representation is exactly the same as integers. Okay, if you have 2 numbers and they're both using the same implicit point, they are already lined up, right? So subtraction and addition and also comparison are basically just exactly the same way as you would do it with regular integers. Signed versus unsigned representation, exactly the same thing. If you want to represent a negative quantity, you just apply 2's complement. No big deal. Okay, we can do that. Multiplication is a little bit harder because it's kind of the same thing as 1.01 in base 10 times 25.005. Okay, if you want to do the exact calculation, then you would multiply 25,005 to 101, and then you shift the point a few times in order to get the point to the right place after the multiplication. Same thing here. Okay, we'll talk about that later. But there's one inherent problem with this type of representation, not from the perspective of a bank. Okay, a bank would look at this type of representation and say, that's good. Okay, because with a bank, when was the last time you have to apply sine and cosine, in a banking type of situation? Probably not a whole lot, right? The only time you have to deal with any type of precision would be the calculation of interest. Okay, because you can have, like 0.05 or something as an interest rate. Okay, but other than that, when you're putting money into the bank, it's usually all in the same units. So there's no big problem here. All right. Would this work well with an astronomer? And why would this not work with an astronomer, who typically has to calculate or at least store the distance between objects in outer space? So what is one thing that you might have noticed about distances to objects in outer space, like distance to the moon, distance to satellites, the distance to the sun, distance to the nearest galaxy, the Andromeda galaxy? Yep, go ahead.
I'm not sure it changes.
It changes, but what about the magnitude?
Yeah, much more.
But you can kind of argue and say, yeah, but the amount of money I have in my bank and how much Bill Gates is worth is also a big difference. So what is the order of magnitude between your saving account and Bill Gates' savings account? Well, it's a lot of orders of magnitude, but give me an idea. How much is he worth?
87 billion.
He's 10 to the 9.
80 something billion?
No, I think he's lost that. That's back in the 90s.
Thanks to Steve, right? Yeah.
He's like, let's say 60.
60. Let's say 100, okay? So let's say Bill Gates is worth 100 billion. B for Bill. Right? And G is for Gates, for Giga, right?
Yeah.
Same unit. Yep, that works out too. Okay. So, and on the other hand, let's say I'm the other person and I'm worth, let's say $100. Okay. Well, just for argument's sake, they're off by 1 billion times. And then you go to an astronomer and say, wow, 1 billion times is a big deal. And the astronomer will look at it and go like, well, at least it has a name. Right? So that's the problem with an astronomer, because they have to deal with quantities that are so different in terms of just the order of magnitude that this is not going to work. Okay? Are you guys understanding what I'm saying? Okay. In other words, if you have a scientific calculator and you have to enter the number of miles between the Milky Way galaxy, or the center of the Milky Way galaxy, and the nearest galaxy, which is the Andromeda galaxy, but without using the scientific notation, you have to enter the entire number as an integer, as a string of just 0 to 9 digits. How long would it take you to enter that? Let's think about it.
Like longer than time.
Longer than you would want to spend time, right?
Yeah.
Okay, so I'm going to ask that question and say, distance from Milky Way to Andromeda.
Yeah, in miles.
2.5 million light years. And how much is that in miles? Okay, I guess I can use
No,
miles.
you can put it in. They'll put it for you. 2.5 light years. Oh, why?
No,
million light years.
Yeah, 2.5 million LYS.
Yeah, 2.5 million light
Equals,
years to-
and it'll give out the
miles.
actual answer.
Sorry?
2.5 million miles to 2.5 million light years to miles. You could do that for.
Yeah, put it in.
Okay. Put it where?
Inside the
Just to
search
Google,
bar.
it'll do it for you.
Yeah.
You do 2.5 million
Or just light years to
light years to miles, and you
Yep.
two
That's
miles.
to meters.
And well, just go back to the search bar. and
On
then
the search
change
bar,
it.
after years,
Yeah, right. Shut
after years, type 2 miles.
2 miles.
Yeah,
There we go.
Okay.
Yep.
Well, actually, it's not too bad, is it?
There you go.
It will just take you like 19 digits.
Yeah, yeah, I'm like, you can't-
But that's really just the closest galaxy. Okay, that's just the closest galaxy. How far is the most distant object that people have detected today?
Oh, 13 light years. Yes, 14 billion light
2.5
years.
billion light years away, right? Which is pretty amazing. You know, if you think about it, if you look through a telescope and see the light from that object, that light, that photon, or that bunch of photons, was emitted 2.5 billion years ago, and your eye is just now registering, that thing. So you can kind of imagine, I mean, that thing is not even there anymore, right? It's not even close to there anymore. Okay, so that's really just amazing. Okay, so when you look at this number and you look at, the order of magnitude between how much I'm worth and Bill Gates is worth, this is a billion that only accounts for the 9 of the 19. And this is one of the closest galaxy. In fact, this is the one that's going to collide with the Milky Way galaxy in, I cannot remember how many years.
It said,
Oh, it says that right there?
hit the back. Well, it said if you hit the back.
Yeah. Yeah, I think it's about, a few billion years or something like that.
Yeah, don't hold
It's a
your
pretty
breath.
long amount.
So we start.
Yep. So the bottom line is astronomers and scientists have to work with quantities that is so different in terms of the order of magnitude. The fixed point representation is not going to help out. Okay. Okay. If that is not going to help, what are we going to do about it? I mean, in terms of small quantities, there are really, really small quantities as well. Okay. What is the mass of a neutrino?
It doesn't have to wait.
Hmm?
In front of the 19 there.
10 to the 32, 10 to the 31. I don't know. Negative 30. Negative 32.
Neutrino.
Oh, negative
Distance between the neutrino and the next galaxy.
Wait, no.
We'll put it in kg, just so that it's something that we can relate to. So we have that number.
That is negative 36 kilograms.
Yep. Where?
Right, just a little bit lower.
Oh, right there.
Nope, not that same one.
Wait.
Second one, right there.
That's gram. Well,
Yeah,
gram
if
is
it's grams,
clear.
you can convert that.
Just do mass of electron is 10 to
If
the
that's what it is in
31.
grams.
I know it's 1.67 times 10 to the negative 31 for
Is
electron.
it wrong? You mentioned no.
Oops. Okay, I should have clicked that. Click mass.
Maybe it's not now.
It is no.
It is
I'm pretty sure that.
It has to be no.
Because it depends
You're
on.
just not asking Google, right?
Side.
Okay, we just did the neutrino up there.
Did it pass it?
Take the link, yeah, go up. Go up.
Just subtract the mass of proton and neutron from the.
Yeah, which is not a whole lot.
Right
An
there.
electron from a neutron. That's
Well, neutrino.
Like my eyes will lock on the word.
Okay,
Yeah.
maybe,
I'm like, this is
maybe we'll do another search.
No, it isn't.
Okay, it's calculated for the first time, so they must have that here.
Well, so, you're
Oh.
venturing onto the internet.
It's in the.
Oh,
Yeah,
it's
yeah.
okay. That's good
Ads.
enough. Okay, okay. They're representing it in electronic volts, a mass of 0.06 electronic volts, which is far less than a billionth of the mass of a proton. Okay, so there goes that B here. That goes Bill. Okay, so the magnitude change of how much a single person is worth compared to the scientific quantities and values is nothing, okay? Because the mass of a proton is also very small, and then on the other hand, you also have to deal with the masses of neutron stars. Okay, so when you look at the mass of a neutrino as opposed to the mass of a neutron star, the change of order of magnitude is like, right? I mean, there's no name, there's no way to pronounce that order of magnitude without resorting to scientific notation. Okay, so that's good. Okay, so now we want to move on to scientific notation, and I'm assuming most of you know what is scientific notation, because most of you, if not all of you, have a TI scientific calculator, right? So what is scientific notation? Okay, so you have a number times 10 to the power of some number. Okay, very good. This is called the mantissa, and this is called the exponent. Okay, exponent flexor. Okay, and this is a floating point number. Now, this is a floating point number already because you can change this quantity, and by doing that, you're changing where this implicit point is. Are we still doing okay so far with number representation? In this case, it's called a floating point representation because by changing the exponent, this number, you can always confine that to 0 to 9.999999. And by changing the exponent, now you can still specify huge range of values in terms of magnitude. Are we doing okay? All right. Okay. So if this is okay, but this is in base 10, right? This is all in base 10 because when you enter a number in a calculator using the scientific notation, you're entering a base 10 number from 0 to 9.9999 something. You can always normalize to a number between 0 and not 10, just the last value before 10. And this exponent is also in base 10. But you can also look at this in a slightly different way. What if I change this to a binary number? And instead of using a base of 10, I change it to a base of 2. And then with the exponent, I'm also going to use a binary representation to represent the exponent in base 2. Would that be doable? Yep, it's just going from base 10 to base 2. But same concept, same idea. Okay. Are there any questions about this part? No questions? Okay. So at this point, it really is just boils down to details. Okay. What exactly is the IEEE double floating point, double precision floating point representation? That's just all details. Now, because it's all details, I'm not going to waste my time to type it up, and I'll refer to the most authoritative, source of this type of thing. Okay. In fact, you can search for that too. IEEE is called a double precision floating point representation, and the first link is always Wikipedia.
Always the most trustworthy.
Well, and double is the one that we want to deal with. So you just make a quick click to it. 64-bit representation. No, that's not it. There we go. Okay, so this is all the details about it. Okay, so if I just zoom all the way out, you can even see a picture, which is really nice. But the bottom line is this equation here. Okay, so I'll just go ahead and zoom in again to the equation. And also the picture here. A floating point number, as in this particular case, the double precision floating point number is chopped up into 3 different parts. Okay, it's a 64-bit thing, but I wouldn't call it a 64-bit number. Okay, because it's broken up into 3 components. The first component, bit 63, which is far left on the picture and is kind of bluish color, is called the sign. Now, in this particular case, okay, a very special case, the sign bit is truly just the sign bit. In other words, if that particular bit is a 0, the quantity is non-negative. If the sign bit is a 1, the quantity is a negative quantity. We are not referring to the exponent, we're referring to the actual quantity being negative or not. So the sign bit is truly indicating whether it is whether it is a negative value or not. Next to it is the exponent, and this is an 11-bit exponent. But it's not really the exponent that you expect it to be. It's not a signed number. This 11-bit as an exponent is actually an unsigned number. To calculate the actual exponent, you have to subtract 1023 from it. So there's an offset to the unsigned value that we use 11 bits to represent. Okay? The 11 bits will give you up to 2047. So the actual quantity would range from negative 1023 to positive 1024. Because the exponent, when you look at the green area, it is an unsigned integer. So 11 bits unsigned will give you values from 0 all the way up to 2047. Okay, but the actual exponent, which is where the mouse pointer is at, is basically this number minus 1023. So that means the actual range of the exponent in base 2 is negative 1023 to positive 1024. Okay, so that's the actual range. Are there any questions about this picture, about the equation up to this point? And the rest is the mantissa, okay? But the mantissa is not called the mantissa, instead it's called the fraction. Now this is one thing that is special about binary numbers. You cannot do this to a base 10 number, but you can do that to a base 2 number. So what happens is the fraction is always, point, there's always an implicit point here, and this one is implicit. And what is actually represented is only this part. Okay? So that means bit 51 is actually this particular bit here as a part of the mantissa. Is that okay? Kind of? Maybe?
So just one more time, it always starts with point 1, and then bit 51 is the number after that.
Yeah, this part is assumed.
Okay.
And the actual bit, when you look at bit 51 in the picture, it is actually representing the second digit on the right-hand side of the point. Yep.
So if it's assumed, that means we're not storing that 1. Right?
We're not storing that 1 because it is implicit.
So then when we go to convert that, where do we pull that 1 from?
Well, you just have to put whatever from bit 0 to bit 51 is, put it here, and then just assume there's a 1 here, and the implicit point is next to it. Yep. Question? Well, don't you guys have one particular question? Like, how do we represent 0 in this case? You cannot represent a 0. Look at that equation. Okay, let's take a look at this equation here. I would take a look at this particular equation. It's actually a bitmap, which is kind of not very nice because it gets fuzzy when I zoom in. But when you look at this equation here, is there any way to represent 0, as in flat 0? There's no way you can represent 0, right? If sign is 0, negative 1 to the power of 0 is 1. Okay, so it's 1 times whatever is following, which means the number is non-negative. When all the bits for the fraction are 0, you still have this 1 here that is a non-zero, right? So you still have at least 1 as the non-zero part, which is this part here. So I take it back. So the implicit point is like this. So it's 1 times, yeah. So it's basically, this part is the other part, but there's still a 1 point that is implicit. Okay. So I shifted it by 1 position. Okay. And then the rest, if this e is a 0, that means the exponent is negative 1023, 2 to the power of negative 1023, which is a pretty small number, but is it 0?
No.
Not 0. Okay? So if you 0 all the bits, yes, the quantity that you're representing is the smallest possible quantity that you can represent using the floating point representation, but it is still not exactly 0. Now, when you go back to true-false representation in C and C++, what is the definition of true?
Anything other than 0.
Anything other than 0. Very good. So that means if you have floating point numbers, you can never be false.
Yeah.
Right.
Is that 2 power e minus 1023? Is that base 2 or base 10?
It doesn't have a suffix, so it's base 10. Yep. All right. So they make a special rule for that.
So
If
how
all
can we
the-
convert to base 2? Because
How do you convert what to
yeah,
base
the
2?
first one they use base 2, is that right? The first part is fraction, they use base 2, and the second.
There's nothing in base 2 in this representation. Everything is in base 10.
The first formula.
This is all in base 10.
First, the
No,
above
that's
one,
fine.
the one above.
The one above it,
Mhm.
the individual bits are in base 2, and that's why there's a suffix of 2 in parentheses here.
And so the another part that we use base 10, how can we do in the processor, increment there?
Okay.
Because the sixth part is base 10.
The
The
second,
last part of the equation, the first
Yeah.
equation is in base 10.
which part?
It's pulling.
All
The exponent is in base 10,
Yeah.
yes. The 1023 is in base 10. E is just E is just a value, right?
2 point something. Yeah.
E is the value represented by the green part, unsigned. Okay? So I'm just going from the perspective of knowing the actual binary representation of a 64-bit double precision floating point number. How do I know what value it is representing? I'm not going backwards yet, okay? Which is the job of your homework assignment. Okay, I'm just going forward. Given a particular bit pattern, what value is it actually representing? Okay? Okay, so I'll give you one particular example. Okay, and this is a 64-bit number, so I'm not going to pick anything that is going to make me work too hard. Okay, so I'm going to say, the sign bit is a 1. Okay, and then followed by, the other 11 bits, and we'll just pick some numbers here. We'll pick something small. Okay, this is going to be a very, very small number. I just want you to kind of give me what is the quantity it is representing. Okay. And we'll just put a 1 here, and then the rest will be all zeros. So we'll have 5, 6, 7, 8, 9, 10, 11. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So there are 11 bits, and it is this particular bit pattern. Nothing really fancy, okay? Nothing really fancy. And then the rest, I would just say the first 3 bits are 1s, and then zeros for the rest. Okay, so that is the bit pattern, the 64-bit pattern that we are dealing with. I want to know what is the value represented by this particular floating point number. So what you do is you plug it into that equation. Okay, you plug it, not the equation, but the formula. So you put a sign in here, which is the exponent of -1. Okay, so -1 to the power of 1 in this case, times. And this is the summation notation, 1 plus, okay, so we'll just do exactly that, okay, 1 plus, and sigma is the summation notation, right? And for the sigma notation, I goes from 1 to 52, so there are 52 bits. And what we do is we look at each individual bit and multiply that by 2 to the power of negative I in this case. So when you look at this number, this one is bit 51, right? And the next one is bit 50, and so on. So what are we dealing with here? I goes from 1 to 52. What is bit 51? Is it a 1 or 0? It's a 1, okay? And what is the multiplier to that thing? What is 2 to the power of
2 negative 1.
Okay, it's just a half, right? And then the next one is bit 50. Is bit 50 a 1 or a 0? It's a 1. And what is the multiplier to it?
1 and 4.
2.
It's a fourth, okay? So we just have one fourth, okay? What about the next one? Bit 49.
0.
It's also a 1, which is this one here. And the multiplier to that is
8.
1/8. Okay, so we have 1/8. The next one is a 16th, but we don't have a 16th because the next bit, which is bit 48, is a 0. So the quantity of 16th is a 0. Okay, so and the rest are all zeros because that's the way I construct the number. Okay, and then we have to don't forget the exponent. So we have to multiply this by by 2 to the power of e minus 1023. E is the value represented by this particular bit pattern, interpreted unsigned. Okay, this is an unsigned number. 1, 2, 4, 8, 16, 7. 1, 2, 4, 8, 16, 32, 64. This is a 128. Okay, so we are dealing with 128 minus 1023. So now we can move on to the next step. Negative 1 to the power of 1 is just negative 1, right? Any number to the power of 1 is itself. This number is, that's a quick calculation, right? Because it is 1 plus 1/2 plus 1/4 plus 1/8, which is 1/7/8. Okay? And for people who use SAE units, this will be a quick calculation because that's based on powers of 2 as well. And then we have the exponent, which is 2 to the power of 128 minus 1023, which is a negative number. What is it?
Negative 895.
895.
95.
Okay. That's it. This is the actual quantity represented by this number in individual digits. Yep.
So how we get the 128 there? How we get the 128 there?
The 128 from the exponent. We have 0, 1, 0, 2, 0, 4, blah, 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 but 128.
So if
128.
So if one is shift to a 1, so it's like a 256.
Sorry?
So if we shift the 1 to a 1 over, so it's a 156.
We don't shift anything. Because according to this equation, you just say e minus 1023 is the exponent of the 2 as a multiplier to the rest of this number. So this is, I'm just literally just applying that formula to the bit pattern that we're dealing with here. Yep.
How do you got 1 over 2, 1 over 4?
How do I get what?
1 over 2.
It's part of the equation.
Yeah.
This one goes to this goes to negative 1 here. 2 to the power of negative 1 is
So the
1/2.
The I, what's the I value? Where's
I
the
goes from
The I
1
goes to the
to
series
2. It's a summation notation.
So the 52 bits is the value is 0, is that right?
Bit 51 has a 1, not bit 52. Bit 52 is already in the exponent portion.
So we
Bit
use
51
51.
is the last digit of the fraction.
So we use the bit 51, is that right?
Not
This
solely.
is bit 51.
Yeah.
So if you go to
And 51 is 52 minus 1. So when I equals 1, we're dealing with this bit here. But when I equals 1, the multiplier to that quantity is 2 to the power of -1, which is 1/2. Yep.
A quick question. On the above of the diagram, it shows a fraction 52. So the 52 is in exponent.
No, the summation part? No, the 52. is-
Okay, are you talking about this bit?
This is summation.
The 52 fraction.
No, so
you talking about this 52?
there's a diagram on that 52 above on top. So under
This is
fraction,
the least significant bit of the exponent.
because they show under a fraction 52 bits, so that
Well,
goes
that's
to
right, because you count from 0. Bit 0 to bit 51 will add up
That's-
to 52 bits.
oh,
Because we always count from 0, unless otherwise noted. Never. Well, unless you're taking a visual basic class, then you count from 1 all the time. Yep.
So for the homework, we're gonna go backwards?
Hmm?
For the homework, we're gonna start from base 10 and go backwards?
Yes.
Okay.
Woo, yay.
Yep. Okay, but before we move on, I want to double check to make sure that I'm not hallucinating and coming up with the wrong values here. Okay, so we'll just go ahead and do this and say this is negative, and then that's 1.875, right? Times 2 to the power of negative that thing. And the next question is, how do we check this? Okay, this is testing how well you know your C and C++. How many people remember what a union is? Anyway.
Did we ever do union?
No, we didn't do
No, we
unions.
didn't do union. Did I know that?
Okay,
No.
okay, we don't have to do unions. Okay, forget unions because I didn't talk about it. There are other ways to do it too. Yep, go ahead.
We from 1 to the left right side. So if we have another 1 there, do we need to go over? So we just go 0.
If we have more ones over here.
Yeah, can you add 1 anywhere after that?
I'm just lazy and I don't want to have to write out a long expression.
Yes. So if we have 1, we have to go through
Yeah.
all.
Yeah,
Just make sure.
because there are 52 possible terms here.
Yeah.
And I don't want to have to write out 52 terms.
Yeah, if by all 0, we don't need to go.
Right, because if they're all zeros, they're not contributing
Yeah.
to the value.
But if the last one is a 1, we have to go through there.
Correct, yes.
Sure.
Yep. Okay, so we want to double check and make sure that I'm not just dreaming and coming up with all this stuff here, and it is not the actual IEEE double precision representation. So how do we check this? Yep.
Alright, so you break it up into the components, get the sign bit, that's gonna be a 1. Then go to the exponent, add 1023 to it, and get that value, convert it to binary, we already know how to do that.
That's one way to do it.
And then get the fraction, and that's 2 to 0 plus 2 to the -1 plus, and we already know how to do that too. So.
I'm just going to abuse GDB to prove this point. How about that?
Okay.
So what I'll do is I'm going to declare a 64-bit integer, just like a regular 64-bit integer. And I'll put in that number just to get a bit pattern into the 64-bit format. Okay? I'll go into GDB, and I'll tell GDB and say, you know what? The address of this thing is really not the address of a 64-bit integer. It is really the address of a double precision floating point number, and print it as such. Well, I did say abuse, right? I didn't say use, I said abuse. Okay, so we'll go ahead and try it out that way. Yep.
So the program is to write a C program then?
You're gonna write a C or C++ program. You can, if you like to structure your program and use classes and whatnot, that's fine. But we'll prove this first. Okay, we just want to double check and make sure that this is actually the correct way of interpreting the bit pattern in a double precision floating point number. Okay. All right. So let's go write a little C program and do most of the work actually in GDB. Okay. Okay, so we'll just call this one, I don't know, F, I'll just call it double, okay? Double.c. I don't really need to include anything other than stdint.h. Now, this particular include file would include the type def or the type definitions of int32 underscore t, int64 underscore t, and so on. So instead of having to remember, oh, a long is 64-bit, I just say I want a 64-bit integer as a type, and I don't have to worry about which platform am I on, is long really 64-bit, and so on and so forth. Okay?
Well, I don't know if this is the same place, but so is that file any different? Is it different from the limits.h? Like,
It is different. I believe it's different. And I changed the font size a little bit, so I'm going to change it back to the full size, or the regular size that we use in this class, because the way it is right now is just a little bit too small. Just want to make it big enough that everyone can see it. Is that okay? Okay. All right. So we'll go ahead and write this program, and we always need a main. So this time I declare a 64-bit integer. Signed or unsigned is not even important, okay? Because I'll show you why it is not even important. And now I just need a single assignment statement to convert that particular bit pattern into hexadecimal, so it's easy to enter it. Because otherwise I will have to do all kinds of stuff to enter it. Okay. To convert this into a hexadecimal number, we group it into chunks of 4, starting from the most significant side, because it's easier to read that way. That's 4-bit, which is an 8. That is 4-bit, which is another 8. Let's see. And then we have these 4 bits being a 0, and then these 4 bits being an E, and the rest are all zeros. Is that making any sense? Okay. It's a table lookup. Okay. You group the bits into chunks of 4, and then you look up a chunk of 4 bits and look at the table to find the hexadecimal digit representing those 4 bits. This is a conversion method that only works when you're converting from a base that is a power of 2 to another base that is to binary, basically, to base 2. Okay? Because 16 is 2 to the power of 4, and that's why we can do it this way. You cannot do it this way when the other base is not a power of 2. So between base 2 and base 10, it's messy, long, and I don't want it to do. All right. So we'll just go ahead and enter this number. 0x, is it 88? 0e? Did I miss something?
12 zeros.
No, the trailing zeros are well. I mean,
880e, and then a whole bunch of zeros after that. Okay, so this is a 64-bit number, 4 bits to a hexadecimal digit, right? So we need 16 digits. This is accounting for 4 of them. I need 12 zeros, okay? And I'm really bad with counting, so I'm gonna leave it up to VI to do the counting by doing this, okay? So I do the escape here. I press 12 on the keyboard. You cannot see it. So 1, 2 on the keyboard, A for append, and then the 0 here, and then press the escape key. Oh, there we go.
How do you do that?
I just started out, right? Okay, so now I want to make sure that there are actually 12 zeros. Just to double check, you can see the cursor position. This is 24, and this one is 12. So we have exactly 12 zeros. So it's always good to be able to double check. Okay.
Procedure for that? Can you just say
The
that one more time?
procedure to do it is 1, 2 on the keyboard, not in editing mode, obviously. So 1, 2, lowercase a for append, and then that will put you into edit mode immediately. You press the 0 to enter 1, 0, and then you press the escape key and say, I'm done with editing. And then whatever you enter during the edit mode will now repeat exactly 12 times. In other words, I have a repetition of 12 append zeros. Okay.
So I have a question.
Yep.
So you do that always 12 times?
Hmm?
So you do that 12 times always?
No, just because I need 12 zeros here. Yep.
Okay, 12. Got you.
All right. So this is just a way for me to enter a particular bit pattern into a 64-bit integer. Okay. I'm not interested in this particular value. I'm interested in the interpretation of this bit pattern using the double precision floating point interpretation. That's what I want to do. Attack, you don't have anything as a double in this program because I'm going to use GDB for that purpose, right? All right, so let's go ahead and do it in GDB.
Why do we need 12 zeros there?
To pad all the least significant digits with all zeros.
Why is the 12 a lot? 51. Why is 12 a lot? 51.
Because those are
after-
in hexadecimal digits. They're in hexadecimal, not in binary.
So we converted 52 to there is 12 zero.
So see,
It's
No.
No, we need 64 digits.
Uh-huh.
Each
There
one
are
of those letters
there are
counts as 4.
52 digits here,
see.
and one is a non-zero, which is the E.
Yeah.
Okay, and there are 4 bits to one hexadecimal digit. So how many zeros do I need to pad?
51,
So
which is
46 zeros.
Not
So you
12,
divided
48?
Yeah, 48 divided by 4.
No,
48 divided by
48
4 is-
bits. How
Yeah.
many hexadecimal digits do I need?
So divided by 4.
Exactly, 12. Magic number.
why is it 48?
Because 48 is 52 minus 4.
So the first 4 we do it is E. The first 48 is E.
When you convert that one
Oh,
to
yeah.
hexadecimal, then you got E.
That 111 is E.
So that
All right.
Yeah. Thanks.
So I have just loaded up, double as a program, ran the one single assignment statement in it, which is not very exciting at all, has nothing to do with floating point number, and I'll just double check and make sure that this is correct. Print /x, which means print in hexadecimal, the value of x. Hey, that looks familiar to us, right? Okay. But where's my floating point number? Where's my double precision floating point number? It's not here. Okay, let's do something about this. Let's say print, but this time I'm going to say translate it into a double. Let's see what happens. Do you think this will give me what I want?
It's going to cast that.
It's going to cast it, which means it will take literally the value represented by 0x, 88, 0e, blah, 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 into an actual value first, and then change the representation and into a double precision representation. Because it's casting the value, it's not casting the representation.
So
That's not going to help.
how about that? You don't lose something?
Okay, if that is, okay, I just want to show you it's not helping. Okay, that's definitely not the number that we're looking at, right? Because just because of this, we know this number cannot have a positive exponent. Okay, it's going to be some negative exponent. We can even guesstimate in base 10, what is the order of magnitude that we should be looking at. Okay, so we're dealing with negative 895 when we use a base of 2. Approximately, it's about 3.3 digits in binary to one decimal digit. So if you just divide this by 3, that'll give you the approximate base 10 exponent, which means we're expecting a value that is 10 to the power of negative 100 or so. Okay, the exact number I don't know, but I know it's about there. Okay, about 100. So that's not what we want. Okay. So let's try something else. Let's take the address of x. Okay, if x is a 64-bit integer, what is %x as a C operator?
So address.
Is the address of a 64-bit integer. Okay, fine. And then we'll tell the compiler and say, pretend it's not. Okay, in other words, we take the address of something, we change the type of what is at that address. Okay, we take the address of a military base and then we say, no, 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 it's a hospital. It's the address of a hospital, and treat it as such. Okay. And then what do you do with a hospital? You send patients to a hospital, right? Okay. So we first take x, take the address of x, which means we have a type of a pointer or an address of a 64-bit integer. And then we say, well, we don't like to look at it that way. I want to look at it as the address of a double precision floating point number. Okay? But it is still an address, it's still a pointer, right? So the extra asterisk on the left-hand side is dereferencing it. But what is it dereferencing? It's not dereferencing a 64-bit integer pointer, it's dereferencing a double precision floating point number pointer, which is going to give me what I want. But this is only one of many ways to get what I want. Okay? And that's the value.
Huh?
It's close.
How much closer?
Okay, but let's just say that we are not convinced this is the number. Let's do the let's do this again, but using a regular calculator. Okay, and we'll turn it into advanced mode. All right, and I cannot see my own numbers back there. Okay, but that's okay. So it's 1.785 times 2 to the power of what again? Negative
894.
895.
Because this is not going to show that.
Like,
You need put the exponent to in parentheses.
Oh, okay. Let's try that again. 1.875 times 2 to the
Is that
power
like-
of negative 895. It doesn't give me enough precision to it. Okay, advanced mode, programming mode. There's no scientific mode. Fine, well,
What are you trying to get it to do?
I'm trying to calculate the exact value and match this.
What's the exact value?
Just go through this equation here. Just do this equation in a scientific calculator.
Just type it into Google, it'll return a result. Yeah, it will, because it has its own
Oh, it has its own
integrated calculator.
Ooh, okay, so we'll Google it then.
Yeah.
20.
1.875 times
Yeah, I can
2 to the power of. Does it use caret as a power 2?
Yes.
Okay. Well, I have to ask because I program in C and C++. Okay, so that's it. Yep, there we go. You got it. Yep. Yay.
Firefly.
Yep. All right. So that means I was not hallucinating when I came up with this value that should be represented by this particular big pattern. Right. So that's the opposite direction of your homework assignment. So are you guys ready for the homework assignment?
Yeah. Absolutely.
Ready? Okay. So let's go take a look at your homework assignment. And you have 1 week to do it. This is a 1 week homework assignment, just like most of the other homework assignments. Okay. So this is your homework assignment, and you have to use the virtual machine to do it, or whatever you do, you have to turn it in so that my script can pick it up and compile and run it. Okay? And some of you, I know who in this class can write this kind of code without running it and check it and turn it in. Silence is like, no one is trying this. Okay. All right. So write a program to convert a real number into a floating point representation, but without using any internal float or double type or any C library other than the ones explicitly allowed, which is none. Okay? And here, this is the detail. So what you want to do is to download this particular file, which I'll do. I'll show you exactly what what it entails. So I'm gonna download this file, save the link. I'll put it into my temp folder. You should put it somewhere and upload it to the virtual machine if you're not using Linux natively. Okay. So after that, I go to my command prompt and just do a tar xzvf. Now you have to do it in your home folder, so you have to kind of follow the instructions. And the file is called, oh, it's not in here because it's in the downloads folder. Tar xzvf, and it's called atof. Where's my file?
Does inferior mean a child process?
Hmm?
Like when it says inferior process killed, does that mean a child process or like a thread?
Where?
When you go back right up there, where
I
like
mean
when
here?
when it exits the GDB,
Oh, right.
inferior means a child process or
I think that's a child process here. You can have multiple child processes.
because I guess it's better than child.
Okay, so I just need to know where it's downloaded to.
But I'm pretty sure Linux allows you to change that.
And it is in the temp folder. Oh, okay, I see. So the temp folder, tar xzvf atof start.tar.gz, and it will unzip into its own little folder, okay? So when it unzip into its own little folder, it will give you 2 C source files, of which you only need to change 1. Okay, so we'll go ahead and take a look at the C source files. atof. Okay, we'll take a look at the main program first. This is your main program, which is one of the many ways to do it. You know, it's just using union instead of the other way to do it. But in this particular case, you know, you are going to take a string, okay, which is in double quotes, and you will convert the scientific notation in base 10 into the double precision floating point representation in binary, and put it into the 64-bit integer member I of u, okay, which is just an integer, okay. I'm just using a different trick to convert from 64-bit integer into a double precision floating point number, and you will convert another one using a different number, okay, and then we'll do the multiplication. So what it should print in this case is u is going to be 1.023 to the power of times 10 to the power of 3, which is 10,023. The second number is 1.25. Oh, that 3 should not be there. But it's 1.25 to the times 10 to the power of -1, which is just 1/8. Okay, that 3 is actually not supposed to be there. I'm gonna have to redo the tar file. And then when you multiply, it'll give you the result of the multiplication. Okay? So we're dealing with about 1,000 and 1/8 here. Okay, so the result should be about 125-ish. Okay. All right. So the third line, the third printf, should print that. Are there any questions about this code? Sort of. No questions about this code? This is the part of the program that you don't need to change. Yep, go ahead. Okay. All right. So this is the part of the program that you don't need to change. So let's take a look at the part where you need to change, which is atof.c. All right. This is it. Okay. This is the shell of the subroutine that you are going to write. Okay. Without using any library functions or any type of double or float casting of any kind. Okay, so you're only allowed to use integer arithmetic operations, bitwise operators, and so on. Okay, you can use any control structure you want. Okay, for loop, conditional statements, recursion, they're all yours. Okay? And you are going to convert what is the string pointed to by PTR into the bit format of a double precision 64-bit number. Okay, so I just want to test it here. Okay, I just want to test it. So I'm going to inject this particular value into here, okay, and see if it does the calculation correctly. Is that okay? So I'm going to inject a value just to test this program to see whether it works or not. So I'm just going to specify x equals to 0x880e and 12 A0 escape. Okay, just like the previous constant. Okay, so when I multiply this number to itself, because it's returning the same number, again and again, it will be 7 point something times 10 to the power of negative 270 something. So when I do it twice, the number may be too small already. So I'm going to change the exponent a little bit. So I'll tweak the number. So instead of a 1 here, I'm going to tweak it and put a 1 over here instead. So that will make the magnitude a lot bigger. So I'm going to have to refigure out the bit pattern and the hexadecimal numbers. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So now the number is no longer 8, 8. This part has to change. The first 4 bits will be a C, and that's the breakoff. So it'll just be C, 0, 0, E, and then a whole bunch of zeros. Okay. So, and plus I also want to do it over here as well. So with a 1 here followed by 10 zeros, what is it actually representing?
Or 1024?
It's basically 2 to the power of 10, which is 1024. So it's no longer 128 here. This time is a lot easier to work with. I wonder why I didn't pick this number to begin with. Right?
Yeah, look at it.
Yeah, yeah. Right? So that would just be 3.75, I think. So it would the first line, the second line will be printing 3.75, and then the last line should be printing 3.75 squared, which is about what, 14-ish, I think. Okay. So it's always important to kind of guesstimate what the program is going to do instead of just running it to find out what it's going to do. Okay. All right. So let's go ahead and save this program. And okay, we have a fine mess here. We have 2 C source code, and this is supposed to be one single program. How are we going to make the executable so we can run the program or debug the program?
Use the make file.
Exactly. And how do you use a make file? You just say make, because the make file has the name of uppercase M-A-K-E-F-I-L-E, which is automatically picked up by the make utility program. So all you have to do, if you change any of the source files, all you have to do is to say make, and it will automatically compile all the necessary components and relink to the executable. Well, spits out unknown command. It's still running though. Which one is it? I think it's still okay. It didn't report that, when I ran it. It's about the SED command. I'm just going to check it. Okay. I lost some of the content. Well, it's still running, so I'm not too concerned at this point, so I'm not going to break our concentration. So we'll just go ahead and run the program and see what it does. Okay, negative 3.75, negative 3.75, and the square of those two numbers is 14.06. I'm so close. All right. So that's what the program is supposed to do, but you will have to parse the string to turn it into the bitwise representation. All right. So what do you think? Now, fortunately, because I know this is not, we are not working for Intel, and I'm not expecting you guys to do all the actual conversion, so you can make certain assumptions about it. The assumption you can make is, first of all, the base 10 exponent has a limited range of from -5 to 5. Okay, so that makes everything fit into like a 64-bit integer, because I don't want to exceed that representation. Then you have to actually deal with counting the you have to do the log and all kinds of stuff like that. You can also assume the base 10 mantissa is only from -10 to 10 exclusively, which means it does not include 10 or -10, but everything in between is a part of the range. Okay. That makes it a lot easier, because you don't have to deal with, oh, but what if I specify 200 as the mantissa? Then you have to do all the shifting in base 10 first, So this saves you all the trouble for doing that. The general format of a floating point number is using this particular description. When you see square brackets, it means optional components. When you see a bar, it is separating alternatives. When you see a plus without the underline, it means at least one of the thing before that. Okay? This is actually a regular expression. When you see an asterisk, it means any number of the things right before that. When you see D italic with underline, it means any digit, 0 to 9. When you see E, it means the letter E all by itself. It's just literally, lowercase e. When you see plus, which is boldface with an underline, it means just literally the plus operator, the minus operator, and the period. So basically anything that is underlined and not in italic is just verbatim. It is just what it is. If you see something that is italic, which is D is the only one that is in italic, it means it can be any digit from 0 to 9. When you see something grouped by square brackets, it means that group is optional. When you see a plus after something, it means whatever is immediately before that has to occur at least once. When you see an asterisk, it means whatever is preceding it can have any number of, including 0. So I'll go ahead and take a closer look at this one. And by the way, this is regular expression. For those of you who have been longing to understand, regular expression, here it is. So what this means is the sign of the floating point number is optional. Okay, you may or may not get the actual sign. It may be a plus, it can be a minus, and you can assume the number that I give you to parse is properly formatted, so you don't have to do error checking and stuff like that. Now, error checking can easily double the size of program, if not more. Okay, so if you don't have to do error checking, it's a whole lot easier. This particular D is not optional. It has to have at least one single digit. And because I'm confining to -10 to +10 exclusively, that means it's only going to be 9 point blah 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 to -9 point blah 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 blah. So that's why this digit is only 1. That simplifies life for you a whole lot. And then there's this decimal point, which is optional. So we are basically looking at this entire group being optional. So within the optional group, after the optional period, you can also have optionally any number of base 10 digits, okay? And you can make an assumption that I won't give you any more than 4 digits, okay? So it's an unspoken, assumption to make your life a whole lot easier, okay? So you can assume, the number of digits after the decimal point is up to 4. So I can give you something like 9.9999 at the most, okay? But that really helps in your case because it really helps to shrink the range of numbers that you have to deal with. This entire component is optional. So I may or may not give you an exponent in base 10. Now, if I don't give you an exponent in base 10, what is the implicit exponent? 0. Yep, because 10 to the power of 0 is 1. Yep. Okay. But if I do give you an exponent, it would start with a lowercase e, followed by optionally a sign, and a particular digit. Now, since I already confined the exponent to -5 to +5 in base 10, that means even though I say here it is a D plus, it's really one single digit D, which also helps to simplify your life a whole lot, a great deal. Okay. So are there any questions about this part? Let's go through some examples. So I'm going to give you some examples that are valid input into this program. All by itself. Valid input, right? Because the sign before is optional, the decimal point part is optional, the exponent is also optional, so that's fine. I can give you that. Okay, the sign is optional, so this one does take advantage of the sign, but there are no other components. I can give you something like that. In other words, I won't give you any more than 4 digits after the decimal point. Okay, so I'm gonna add that to the assignment description so that you guys can count on it as a part of the restriction. I can give you something like this, right? Because the actual digits after the decimal point is optional within that group. What about this? Can I give you something like that according to the regular expression? No, I cannot, because I can only give you one single digit before the decimal point. So this one, you don't have to deal with. What about this? But is it properly formatted? No, because if I specify a lowercase e, I have to give you some digits after that. So this is not okay. I cannot give you that. What about this? I can give you that, right? So this is actually just specified 200. Any other format that you want to kind of test it with?
+1. +1.
+1 is definitely something that I can give you. Okay. So the full up, the most complicated thing that you can possibly have to parse would be a sign, a digit, which I have to give you, decimal point, up to 4 digits after the decimal point, 2, 3, 4, 5, an exponent, and a sign to the exponent itself, and I can give you -5 to +5.
Can you do 1 point e power -5 times
1 point. Yep. 1 point e, and then what?
and in power 5?
Like that?
Yeah.
I can give you that.
Yeah, the 1 point, which means 1.0 or?
Yep. That's just 1.0 times 10 to the power of 5. So everything is in base 10 here. The first thing you have to do is to convert the base to the individual components first. Are there any questions? How would you? Okay, go ahead.
Can you use IOString?
That would be a library. Okay, it depends on. No, you don't need to use IOStream.
From a file, right?
Yeah, you cannot use a string stream, which would make this trivial. Yep. But you didn't mean that. You meant something else.
I meant, can I write it using like C++ commands?
The restriction is you cannot use any libraries. So everything has to be your code. You can use arrays. You can use, but you cannot make calls to anything that you do not write.
So you can't use cout.
Hmm?
There's no cout or anything.
If you prefer to use cout for debugging purposes, you can do that. You just have to take out those lines before you turn it in.
Okay.
I personally do not like cout or printf for debugging purposes. GDB, can be used, should be used for debugging purposes.
Yeah.
But you can use cout for printing purposes, but not for the actual logic of converting.
Yeah, you said if you do that, you have to almost know.
Hmm?
If you use cout for debugging, you almost have to know, because you have to be expecting it at close to.
Right. Okay, so how are you guys going to structure this particular program? I would write this, bottom up. Okay, we are running out of time, so I'm gonna continue the discussion at the lab. But one way to write this program is go from the bottom up. In other words, I will start with, a subroutine to take a string of base 10 numbers and just convert it into the value represented by the base 10 number as a string. Okay, I would start with that. Because potentially you can have 1, 2, 3 components of that. So that would be a useful subroutine to have. It's basically just, okay, I want to see if there's a base 10 number here. Now, if you try to run it on here, you can just come back and say, no, this is not a base 10 number. Then you can do something else and check what it is. So that would be the first thing I do is just a base 10 conversion. And after this single digit here, you can check, is there a decimal point? If there's a decimal point, then you just flow to a different part of your program. If there's no decimal point and you see an E or it's the end of string already, then you can also, act appropriately. Okay. Are there any questions? Is anyone familiar with a finite state machine? FSM. A little bit? Okay. Every regular expression can be recognized by a finite state machine. So if you know how to deal with a finite state machine, parsing that particular regular expression is actually possible using a finite state machine, which may or may not help. Okay, so that's the end of the lecture. It's all recorded. I will upload the video as soon as possible, and then we'll head out to the lab at about. I'll give you guys 10 minutes or so. And then at the lab, I'll give you guys some additional ideas of how to implement a program like this.